Good afternoon. So we are continuing with the different criteria functions which are used for designing of the linear discriminator. So far we have discussed about three types of criteria functions. The first one was the perceptron criteria. Then we have talked about the relaxation criteria, and the last one we have said was the minimum squared error criteria. So what I have seen in case of perceptron criteria is that you define a criteria function which is given by Jp, which is nothing but minus A transpose y for all y which are misclassified. So this was the perceptron criteria function. And our aim was that we wanted to find out the weight vector A which will actually classify all the training samples properly. Okay. So when all the training samples are classified properly, in that case this criteria function, the perceptron criteria function Jp has to be equal to 0, which is the minimum value, and if any sample is misclassified by the weight vector A, then the criteria function Jp will be greater than 0. Okay. And following this, what we have done is we have taken the gradient of this criteria function Jp with respect to A, and then we have followed the gradient descent procedure to come to a particular solution, to come to the solution of the weight vector A. And accordingly, we had the weight updation rule or the perceptron algorithm, which was given like this, that A0 was initially selected arbitrarily, and then in every iteration Ak plus 1 was obtained from the previous value Ak following the gradient descent procedure, and it was simply Ak plus eta times summation of y for all y which are misclassified. And there we have seen the problem with this algorithm is that because we have to take the summation of all the misclassified samples, so the amount of memory which is required for execution of this particular algorithm is quite high. So we had a sequential version of this algorithm, where the first step, that is selecting A0 arbitrarily, remains the same, and what you are doing is you are taking the samples one by one, and whenever a sample is misclassified, instead of trying to aggregate all the misclassified samples together, whenever a sample is misclassified, immediately you go for updation of the weight vector A. So accordingly, our weight updation rule was sample by sample. So if the kth sample is misclassified, then immediately you update the weight vector following this updation rule, that is Ak plus 1 will be Ak plus eta times Yk, where this Yk is the sample which is misclassified by the weight vector Ak, and eta we said that this is the convergence factor. Okay. Similarly, we have also talked about the relaxation procedure or the relaxation criteria. Where the problem faced with the perceptron criteria, that is, we can have a solution vector which is just on the boundary. Okay. So if you get a solution vector which is just on the boundary, then it is quite likely that if I use that vector for classification of unknown samples, then the probability of misclassification or the probability of error will be quite high. So what we want is that weight vector should be well within the solution region. Okay. So that problem is solved by this perceptron criteria, by this relaxation criteria, and in the relaxation criteria, the criteria function was modified as JRA, which is half of A transpose y minus B square upon modulus of y square. Again here this vector y is misclassified. So, it has to be done for all y misclassified. Okay. But our design rule remained the same, that is, you take the gradient of this with respect to a and then follow the gradient descent procedure starting from some initial weight vector which is chosen arbitrarily. And so, we have this algorithm, relaxation algorithm, which is given as a0 is chosen arbitrary, and then we have this iterative approach, that is ak plus 1 will be given by ak plus eta times summation of b minus ak transpose y upon mod of y square into y for all y misclassified. And then we have seen that the corresponding sequential version, where the updation rule is modified as ak plus 1 is equal to ak plus eta times b minus ak transpose yk upon mod of yk square into yk, where yk is the sample which is misclassified by the weight vector ak. Okay. And then we have said that both these criteria functions, whether it is perceptron criteria or the relaxation criteria, these are useful when the samples are linearly separable or the classes are linearly separable, in the sense that given the set of training samples from two classes, say omega 1 and omega 2, I should be able to draw a boundary between these two classes, where this boundary is a linear boundary. So, in case of 2 dimension, it has to be a straight line. In case of 3 dimension, it has to be a plane. For multi dimensions, it has to be hyperplane. So, it is actually a linear boundary between the two classes omega 1 and omega 2. But if the classes are not linearly separable, then neither the perceptron criteria based algorithm nor the relaxation criteria based algorithm, they will give you a unique solution, and the algorithm will never converge. So, in such case, we have this minimum squared error algorithm or MSE criteria function, where the criteria function is based on an error measure, where error is nothing but ya minus b, where y is the collection of all the training samples. Okay. A is the weight vector and b is called a margin vector. Okay. So, for this MSE criteria, the aim is to reduce square of this error or to minimize the square of this error. Okay. So, accordingly, you define the squared error criteria, which is given by Js as a function of a, which is nothing but mod of ya minus b squared, and I can expand it as a transpose yi minus bi square of this, take the summation over all the samples I is equal to 1 to n if I have n number of training samples. Okay. And then again, if I take the gradient descent procedure or going for that pseudo inverse concept, I get a solution which is given by a is equal to y plus b, where this y plus is actually pseudo inverse of y. Okay. And then we have said that we can still have an iterative algorithm following the gradient descent procedure, and in which case the iterative algorithm will be similar to the algorithms that we have said earlier, that is perceptron criteria or relaxation criteria. Here again our initial weight vector A0, this will be chosen arbitrarily, and in every iteration step A will be modified as AK plus 1 is equal to AK minus eta times Y transpose Y AK minus B. Okay. But still you find that here we are considering all the samples together to find out the solution vector. So, again the problem of memory and working with large matrices. So, we can also have in the same manner a sequential version of this iterative algorithm, and in the sequential version of the iterative algorithm, the iteration step will be modified as A k plus 1 is equal to A k plus eta times B k minus A k transpose Y k into Y k. Okay. So, you find that we can go for a sequential algorithm from this updation state, from this updation step, which actually considers all the samples together. Okay. Now, again this iterative algorithm or the mean square error criteria function based iterative algorithm to find out a solution vector is problematic in the sense that we have said that the perceptron criteria and the relaxation criteria are useful when the classes are linearly separable. If the classes are not linearly separable, in that case we can go for this minimum squared error based criteria function. But if I have a problem where the classes are actually linearly separable, but because we do not know beforehand whether the classes are linearly separable or not, so a safest approach will be that you go for minimum squared error criteria based criteria function based approach to get your solution vector A. But the problem here is, even if the classes are linearly separable, it is not guaranteed that linear this minimum squared error based criteria function based algorithm will give you an weight vector which will linearly separate the two classes, or it is not guaranteed that I will have a linear boundary between the two classes, okay, or the samples from two different classes will be put into two different regions. Okay. So, I can have a situation something like this, that even if I have the samples belonging to two classes which are given like this, suppose this is a set of samples which actually belongs to say class omega 1, and I can have a set of samples over here, let me use different symbol, something like this, where these samples actually belong to class omega 2. Okay. Now, here you find that I can easily, so these are my two features x1 and x2. So, I have a two-dimensional feature vector. Now, here you find that it is quite easy to find out that I can have a line separating these two classes. Okay. So, because these are linearly separable, so I should get an weight vector which will actually define this line. But when I go for this mean square error based criteria function, I may land up with a boundary something like this. Okay. Because in case of mean square error based criteria function, it tries to minimize the sum of squared distances of the different feature vectors from the line. Okay. So, as a result, the boundary that you get, that may not separate the samples belonging to two different classes. Okay. So, how do we solve this particular problem? So, though this MSE or minimum squared error based criteria function may lead to this kind of problem, however, it can be shown that if the classes are really linearly separable, then it is possible to have some A, weight vector A, and some weight vector B, where ya minus b or ya will be is equal to b, where this b is greater than 0. Okay. We didn't have any such constant when we talked about the minimum squared error criteria function. Okay. So, if the classes are actually linearly separable, in that case it is possible to have an weight vector A and a margin vector B, where this equation will be satisfied, that is ya is equal to b, where b is greater than 0. So, when I say b is greater than 0, that means every component of b is greater than 0, okay, because b is a margin vector. So, you say that every component, and this will have n number of components if I have n number of samples. Okay. So, when I say this margin vector b is greater than 0, then every component of this margin vector is greater than 0. And assuming this, we have to define a criteria function. Earlier we have defined the criteria function as a function of only the weight vector A, because our aim was to select the weight vector. But now what we have to do is we have to select both A and B, because we don't know that which particular B will satisfy this equation for a particular A. So, we have to try to update or iterate on both A and B. Okay. So, again we have to start with an initial value of A and initial value of B. Okay. Then we have to update on B, and for every updated value of B or for every iterated value of B, we can find out what is the corresponding A. Okay. So, while doing that, when we update B, we have to keep in mind that in none of the cases any component of B can be less than 0. We always have to maintain that every component of B will be greater than 0. And that can be satisfied if we start with a B with every component positive, and while modification of B, we will allow only a component of B to be incremented, not to be reduced, because if we allow a component of B to be reduced, then there is a possibility that a component of B may come down below 0, okay, which will not satisfy this condition. So, while updation, we have to keep in mind that we will always allow increment of B, but we will not allow reduction of B. Yeah, because that is a matter of scale factor. I have ya is equal to b. Okay. So, what I am saying is I will always increment the value of b, I will not reduce the value of b, because reduction of value of b may lead to a condition that a component of b, say bi, may be less than 0. So, this is what I will not permit. I will always increment the value of b. Okay. And the scale factor that is incorporated, that will be reflected in the corresponding value of a in the weight vector. Is that okay? So, when I do that, I will redefine my criteria function, that is Js. Earlier it was defined as a function of only A. Now, I have to define this as a function of both A and B, where A is the weight vector and B is the margin vector. Okay. However, the definition will remain the same, that JSAB, which is ya minus b squared. Okay. Fixed, that was fixed. In MSE algorithm, our assumption was that the margin vector is fixed, and for a given margin vector, we are trying to find out a value of weight vector. Okay. So, the problem that we faced, that whenever we fix the margin vector, because we never ensured that this condition will be satisfied, so accordingly we could have got a boundary something like this. It is still a linear boundary. So, this boundary ensures that your sum of squared error will be minimum, but this does not ensure that the classes are actually linearly separated. Okay. So, if the classes are linearly separable, then we have said that we can have a solution of this form, ya is equal to b, where b is greater than 0. Okay. So, we will take the different margin vectors which are greater than 0, and then find out the corresponding value of A. Okay. So, while doing so, we start with an initial margin vector and then go on updating the margin vector with the aim to come to a proper solution. Okay. So, this is what we have. This is our criteria function, squared error criteria function, which is given by JSAB is equal to YA minus B. Take the square of the modulus of this error. Okay. Then this error function, we have to take the gradient once with respect to A and then with respect to B, because we want to update both. Okay. So, if I take the gradient of this JS with respect to A, okay, the solution, the gradient with respect to A is what we have seen earlier, that 2y transpose into YA minus B. Okay. This is what we have seen earlier. And if I take the gradient with respect to B, then the gradient with respect to B is minus 2YA minus B. Okay. Now, once we obtain any value of B, then the corresponding value of A can be obtained as, so for any B, the corresponding weight vector A can be obtained as Y pseudo inverse B, or we can go in for the same iteration which we have done when we discussed about the mean square error algorithm. Okay. If we are not sure that this pseudo inverse is non-singular, because if the pseudo inverse is singular, we cannot have if Y transpose Y inverse is singular, then we cannot compute the pseudo inverse. Okay. So, for computation of A, either we can go for this if we are sure that Y transpose Y inverse is not singular, or we can employ the same iterative algorithm that we have discussed earlier. Okay. So, here our main aim is that we have to find out a proper value of B by following the gradient descent procedure with the help of the gradient of Js with respect to B. Okay. And while doing so, as we said that we have to ensure that none of the components of B can fall below 0, and that is what we said, that we can only allow increment of the components of B. We cannot allow reduction of the components of B. So, if I want to do that, in that case, at every iteration I can have Bk plus 1, which is same as the same gradient descent procedure, Bk minus eta times, that is rate of convergence, half of gradient of Js with respect to B minus modulus of gradient of Js with respect to B. Okay. So, here you find that because to obtain Bk plus 1, we are subtracting from Bk this quantity. Okay. So, if gradient of Js with respect to B is positive, then what we are ensuring is that this total quantity will be equal to 0. Okay. Whereas, if gradient of Js with respect to B is negative, okay, so here it is minus, here it is also minus. So, I get a negative quantity which is twice of gradient of Js with respect to B. So, to nullify this factor 2, you incorporate this half, okay, and here it is negative, here also it is negative. So, overall you get a positive term. So, effectively what I am doing is, to obtain Bk plus 1 from Bk, to Bk I am adding a quantity. Okay, I am not subtracting any quantity from Bk to get Bk plus 1. So, that ensures that your Bk plus 1 can be at most greater than Bk. It can never be less than Bk. Okay. So, by this step we are ensuring that none of the elements of the margin vector B will be reduced at any step of iteration. And since we are ensuring that it will not be reduced in any steps of iteration, so the possibility of having a component of margin vector B which is less than 0 will not arise. Okay. So our iteration algorithm on B will be same as before, that we will have a B0 greater than 0 but otherwise arbitrary. Okay.
So grad B JS modulus, is it scalar or vector?
Gradient of
Is it the modulus, is it the magnitude of the gradient vector?
it is magnitude of every component of the gradient vector. What I am saying is every component, it is not modulus.
So it is the vector.
It is a vector. It is a vector only with the positive components. Okay.
The vector is minus B1, then minus B2, B3.
Yeah, it will be
plus B1
plus B2, B3. Yeah. Is that okay? So the iterative algorithm will be something like this, that B0 will be greater than 0, which is initially chosen, but otherwise it is arbitrary. Okay. And at every step, this Bk plus 1 will be Bk minus eta times half gradient of Bjs minus modulus of gradient Js with respect to B. Okay. So once I have a particular value of B, I can use that B to compute the value of A, either making use of the pseudo inverse or following the another iterative algorithm for obtaining A by using the gradient descent procedure with gradient of Js with respect to A. That is similar to what we have discussed in our last class. Okay. And by doing this, because we are ensuring that B will always remain greater than 0. So it is quite likely that even for linearly separable cases, we will get a solution vector which will actually linearly separate between the two sets of samples belonging to two different classes. Okay. Now all these different criteria functions that we have discussed so far, whether it is perceptron criteria or relaxation criteria or this minimum squared error criteria, in all these cases we have assumed that we have just two different classes, omega 1 and omega 2. Okay. And our criteria was that if A transpose Y is greater than 0, the sample belongs to one class. If it is less than 0, it belongs to another class. Or if A transpose Y is greater than B, it belongs to one class. If A transpose Y is less than B, it belongs to another class. Right? Now the question is how to generalize this in a multi-category case, because in all practical situations we will have multiple number of classes, not that we will have only two classes. Okay. And that is what is the essence of a linear machine that we have said earlier. That is, for every class omega I, okay, we have a discriminant function defined as Jix, okay, where this Jix is nothing but Wi transpose x plus Wi naught. Sorry. Okay. So this is the linear equation or the linear discriminant function for every class I, right? So for given any unknown sample x, I have to compute this discriminant function for all values of I varying from 1 to c, if c is the number of classes. Then for whichever I, Gix is maximum, we have to assign or you have to classify x to that particular class. Okay. So we have something like this, that we have this G1 G2 like this. If there are C number of classes, we have this discriminant function GC, then given a vector x, the vector x will be fed to the discriminant functions of all the classes. Okay. Then I have a max selector. Okay. All these outputs come to this max selector, and then max selector, depending upon whichever discriminant function gives you the maximum value, this gives you the class identification. Right? And this is what we have said, it is a linear machine. Okay. And we have seen earlier that following the Bayes decision theory, if I know what is the parametric form of the probability density functions of the samples belonging to different classes, then following Bayes minimum error rate classification or minimum risk classification, we can obtain the classifiers or we can obtain the discriminant functions for different classes. Okay. And there we have discussed about the different situations when this discriminant function can be a linear discriminant function, or when this discriminant function will be a quadratic discriminant function, right? But now we are talking about the non-parametric cases. That is, we don't know that what is the probability density function of the samples belonging to different classes. So whether it is possible to have algorithms like these gradient descent procedures to have this sort of linear machine which can classify and sample to one of the C different classes. Okay. So here we find that our condition is something like this, that if I get that GIX, okay, where x is the sample vector, GIX is the discriminant function corresponding to the class omega I. Okay. So if GIX is greater than GJX, okay, for all j not equal to I. Okay. So if GIX is greater than GJX for all j not equal to I, this indicates that x belongs to class omega I, because GIX is maximum among all the discriminant functions. Okay. So this indicates that the sample x belongs to class omega I, right? Or in other words, if I expand this, it simply becomes AI transpose y, okay, where this y is the augmented vector x by adding 1 to it. Okay. So AI transpose y is greater than AJ transpose y, okay, again for all j not equal to I. So that is the condition that this sample x or sample y, augmented sample y, that belongs to class omega I. Okay. And since we are having C number of classes, that is I and j, that can vary from 1 to C. So you find that for a particular value of I, when I have this condition that j is not equal to I for all values of j, okay. So this j will assume every value from 1 to C except I. That means j can have C minus 1 number of values. Okay. So that one which is left out, that is equal to I. So this inequality, that AI transpose y greater than AJ transpose y for all j not equal to I, this is actually equivalent to C minus 1 number of inequalities. Is that okay? So, in all those inequalities, I had to have this particular condition true, that suppose I is equal to 1. Okay. Say A1 transpose Y must be greater than A2 transpose Y, A1 transpose Y must be greater than A3 transpose Y, A1 transpose Y must be greater than A4 transpose Y, and so on up to A transpose Y must be greater than AC transpose Y. Then only I can say that this sample Y or the corresponding sample X that belongs to class omega 1. Okay. So, this equation actually corresponds to, for all values of j, C minus 1 number of inequalities. Okay. Whether it is possible to have an unified approach to take care of this C minus 1 number of inequalities simultaneously and give me C number of weight vectors A1, A2, A3, A4 up to AC. Okay. So, over here you find that, let us take a specific case that I is equal to 1. Okay. So, I want that A1 transpose Y must be greater than AJ transpose Y, okay, for Y varying from 2, 3 up to C minus 1. Okay, later on we will generalize. So, I take a particular value of I which is equal to 1. Okay. So, we find that all these C minus 1 number of inequalities can be put in an unified approach if I take a C into D hat dimensional weight vector. C minus 1, C minus 1, yeah, sorry, 2 to C, right, it is 2 to C, not C minus 1, total number of inequalities is C minus 1, okay. So, all these inequalities can be put in an unified form in a single expression if I consider a C D hat dimensional weight vector. Okay. I am taking the same terminology which we used earlier, that my weight vector is actually d dimensional. Okay. So, after appending 1, it becomes d plus 1 dimensional. So, that d plus 1 we are taking as d hat. Okay. So, I take a d C into d hat dimensional weight vector. Let us say this weight vector is alpha. Okay. Now, what is this alpha? This alpha will be nothing but A1, A2, A3 up to AC. This is my weight vector alpha. Each of these weight vectors A1, A2, A3 up to AC, each of them are actually d hat dimensional. Okay. I have C number of such weight vectors. So, that overall dimension of this vector alpha is C into d hat. Thank you. J equal to 2 to C. Okay. So, this overall vector that becomes C into d hat dimensional. Okay. So, we can think that this particular weight vector, if I have this condition that A1 transpose Y greater than AJ transpose Y for all values of j varying from 2 to C. Okay. So, I can equivalently say that effectively this C into d hat dimensional weight vector alpha will properly classify all the C minus 1 number of feature vectors, where the feature vectors will be of the form, say, let me put it as eta 1 2, which is nothing but y minus y 0 0 0 eta 1 3 will be y 0 minus y 0 0 0 it will continue like this. Eta 1 c will be is equal to y 0 0 0 minus y. Okay. What this 0 actually means that this is a column vector of dimension d hat. Okay. Y is obviously a column vector of dimension d hat. Minus 1 y is also a column vector of dimension d hat. 0 is also a column vector of dimension d hat where every component is equal to 0. Okay. So, as there are c number of such vectors, every vector having a dimensionality of d hat. Okay. So, the overall dimension of these vectors eta 1 2 or eta 1 3 up to eta 1 c, each of them are of dimension c into d hat. Is that okay? So, this inequality that A 1 transpose y greater than A j transpose y for j varying from 2 to c, okay, it is equivalent to saying that alpha transpose eta 1 2 is greater than 0. Is it not? If I put these two side by side, okay. So, let us take these two vectors side by side. Alpha is y a1, a2, a3 up to ac. Eta 1 2 is y minus y, then all components are 0. So, if I take alpha transpose eta 1 2, okay, that computation will be equivalent to a1 transpose y minus a2 transpose y. Okay. Rest of the components in eta 1 2 are 0. So, that corresponding vector multiplication will have null effect, will not have any effect on the result. Is that okay? So, if I take alpha transpose eta 1 2, that is simply a1 transpose y minus a2 transpose y, right. Similarly, alpha transpose eta 1 3, that will be simply a1 transpose y minus a3 transpose y. Is that okay? Similarly, alpha transpose eta 1 c, it will be simply a1 transpose y minus ac transpose y. Okay. So, this condition that a1 transpose y greater than aj transpose y or a1 transpose y minus aj transpose y greater than 0 for all the values of j, for y to be classified to class omega 1, that is equivalent to saying that this weight vector alpha properly classifies all these c minus 1 number of feature vectors, okay, where these feature vectors are actually generated from the original feature vector y. So, you find that the overall data that we are generating over here, that increases dramatically, and that is quite obvious because from a from a two category case, we are moving to C category case. So, your computation obviously will be C-fold. Okay. So, for every feature vector y, I am generating C minus 1 number of feature vectors, right, where the dimensionality of the feature vector, each of these feature vectors is also being incremented by a factor C. Okay. Initially, vector y is of dimensional d hat. Now, each of them are of dimension C into d hat. Okay. So, the dimensionality is increasing by the number of classes that we have, and the number of vectors for every original vector is also being increased by a factor c into c minus 1. Okay. So, the amount of data that we are generating, that becomes quite high. Okay. So, this is what we have considered for a particular case by assuming I is equal to 1. Okay. In general, a feature vector eta ij will be something like this, that I will have these vectors having components 0, ith component will be equal to y, jth component will be minus y, then followed by zeros again. Okay, where this is my ith component and this is my jth component. Is that okay? And this alpha transpose eta ij greater than 0, that is equivalent to, if you follow from here, it will simply be ai transpose y minus aj transpose y, that will be greater than 0. Okay. So, if this condition is satisfied for all values of j not is equal to I, then we say that the sample y actually belongs to class omega I, it does not belong to class omega j. Okay. So, when I have this sort of formulation, that alpha transpose eta ij, okay, for every such inequality, I actually have the weight vectors corresponding to discriminant functions of two different classes omega I and omega j involved in it. Okay. And for proper classification of any sample y, I must have that alpha transpose eta ij must be greater than 0. That means ai transpose y minus aj transpose y must be greater than 0. Okay. So, if I find that this condition is not satisfied for any value of y, for any sample y, then I have to modify actually two weight vectors. Not only ai, I also have to modify aj. Okay. Because both of them are responsible. In earlier case, because it was a 2-class problem, so I had a single weight vector. So, I have to decide whether to modify that weight vector. If it is to be modified, in which way it has to be modified. Okay. Now, I have two weight vectors involved, one for the discriminant function of class omega I and the other one for the discriminant function of class omega j. So, anytime any sample is misclassified by alpha, I have to modify both these weight vectors ai and aj, okay, involved in that particular eta ij. So, the weight updation or weight vector updation rule in this case can be simply like this. Initially, I assume that ai 0 is arbitrary for all I. Okay. That means, for every class, I assume an arbitrary weight vector initially, right? And then for any vector which is misclassified. So, with the help of this initial weight vector, I have to form initial alpha, okay, which is just concatenation of all these different weight vectors. Using that, I have to go for classification of the samples, or the samples are to be modified in this form. Okay. Whenever I know that a sample belongs to class omega I, so for every such I have to generate eta ij, where the ith component will be equal to y and the jth component will be minus y. So, I have to generate eta I1, I have to generate eta I2, I have to generate eta I3, I have to generate up to eta IC. So, for each of these samples, I have to generate c minus 1 number of sample vectors. Okay. And I have to ensure that each of those modified sample vectors are properly classified by the corresponding alpha. If any of those samples is not properly classified by alpha, then I have to modify both AI as well as AJ. Okay. So, that weight updation rule will be AI k plus 1 will be is equal to AI k plus yk, where this is the sample which is misclassified. Okay. And this is what we have obtained using our perceptron criteria earlier. Okay. This expression is same. So, we are incrementing AI in a particular direction. AJ has to be incremented in a negative direction, because we want to penalize AJ, okay, whereas we want to reward AI. Okay. And jk plus 1, for this the weight updation rule will be, this will be simply ajk minus yk. Okay. So, you find that only two weight vectors we are updating, one is AI and AJ. Okay. For every eta ij which is misclassified. Okay. And all other weight vectors will say that AL k plus 1 will remain as AL k, where L is not equal to I and L is not equal to J. Okay. So, only the ith weight vector and the jth weight vector, these two we are modifying. Okay. Modification of ith vector follows the same updation rule that we have obtained in the perceptron criteria. Okay. Modification of the jth weight vector AJ, similar updation rule, but instead of incrementing, we are decrementing it. Okay. So, AI is actually rewarded, AJ is penalized. All other weight vectors other than AI and AJ, they remain unchanged, because these weight vectors really does not take part to tell us whether alpha transpose eta ij is greater than 0 or not. Okay. These weight vectors do not tell us anything about this. Only the weight vectors AI and AJ decide whether this condition will be satisfied or not. Is that okay? So, we are keeping ALK plus 1 is equal to ALK for all values of L which is not equal to I and not equal to J. Okay. And this kind of construction, because you find that every time from AI we are constructing this weight vector alpha, okay, and for every sample y we are constructing alpha eta ij. Okay. This kind of construction is what is known as Kessler's construction. Yeah. Yeah. Yeah, one is sufficient, but there is nothing wrong if you do both of them together. Okay, because our aim is that we want to have AI transpose y minus AJ transpose y greater than 0. So, you increment one, reduce the other one, so that this condition is reached quite fast. Is that okay? If you do not do this, maybe the number of iterations that will be taken will be more, nothing else. Okay. So, let us stop here today. Thank you.